video under design of steel structures according to EISC. Still, we are talking about member stability bracing, and today I'm going to have an example on what I have already explained in the previous lecture related to member stability bracings. So let's go and see how we can start with this. We're going to take and talk about one example that is already in the textbook, and we are going to find that this example is talking about stability bracing for frame. So here, a structure composed of three rigid frames must be stabilized by diagonal bracing in one of the frames. So this means that we are having three different panels. We have three different panels, and we want to stabilize two of three different panels by bracing. So take care of this word, which is three. Rigid frames must be stabilized by diagonal bracing in one of the frames. And so this bracing is going to be responsible for providing the stability for the three rigid frames. The braced frame is shown in this figure, as you can see it here. The height is 18 feet, and the span width is 45 feet. We have gravity loading only, which is 0.9 foot, 0.9 kibs per foot. And as you can see, we do not have any lateral forces, so we do not have any lateral forces, just we have gravity forces. And we need to provide diagonal bracing, as you can see here. The loading is the same for all frames. This means that the three frames are going to be loaded with the same value of the ultimate intensity loading. We're going to use A36 steel. Okay, use A36 steel. And determine the required cross-section area for the bracing. So we need to know what is the cross-sectional area of the bracing that we are going to develop. Use load and resistance factor design, so we're going to use LRFD in our case. Okay, so now we have some information about the example. Let's go and apply what we have, the knowledge that we have accumulated in the last lecture regarding stability bracing. Okay. First of all, the total vertical load to be stabilized, it is the most important thing to know how much vertical load required strength if we are going to talk about this. We have three spans, and we are going to provide one lateral stability bracing, or sorry, stability bracing is going to be provided in one panel. So we need to know how much vertical load is going to be stabilized, because as we said, stability bracing is all about the gravity load. The main input parameter for us is the gravity load. So here PR is going to be the summation of all the vertical loads, which is 0.9 times 45, 0.9 times 45, which is the intensity loading that already we have in the example, times 3, which means that three different types or three different spans. From EISC equation 6-1, this is related to column. So take care, even that we are talking about frame, but this frame, what we want to provide for it is stability for the columns here. And this stability for the column, it is going to be, if we have moment on the column, and we have axial forces, so it is going to be treated as being column in this case, okay? But actually here we do not have anything related to, or we can say if we want to provide the stability bracing for the frame, then we are providing stability bracing for column, okay, for the columns. So we need the columns to have stability against any, based on the gravity loading that is being applied. Okay. So in this case, we are going to provide or use the equation that is related to, this is, if you remember, it is related to column, okay, related to columns. Okay, And in this case, we are going to find that PBR, which is the lateral shear, okay, lateral shear strength to be resisted is going to be 0.004 PR. As I said before, this in 2016 edition of AISC, it is supposedly to reach 0.005. Okay, so do not be confused if you find it in the code with 0.005. And 121.5, it is the total gravity load or the total vertical load that is being stabilized. So we have 0.486 kips. If we consider both braces to be tension-only, remember, what is the meaning of this? We're going to claim that here, if we're going to provide the stability bracing for our structure, we're going to assume that one of them is going to work always in tension. If the structure wants to move in this direction, for example, this bracing is going to resist by tension. And if it is going to move in this direction, for example, this bracing here is going to resist in tension. So we are going to neglect the contribution of the bracing or diagonal bracing in compression. However, we are going to say that all the stability is going to be provided, all lateral stability is going to be provided based on tension on the behavior of the member. Okay? So this is the meaning of, if we consider both braces to be tension-only members, then the entire force must be resisted by one brace. That's right. So if the load is coming from this direction, actually there is no lateral loading here. The lateral loading that I'm talking about, it is supposed to be the lateral shear strength, which is 0.004 PR here. If we consider it as the force that need to be resisted for stability, then in this case, if we have bracing A and bracing B, in this case, bracing A is going to resist all the load. Okay, but if the same loading is going to be applied from the right, as you can see, then bracing B is going to be used for resisting or providing the lateral shear strength in this case. Okay. Because PBR is the horizontal component of the brace forces, okay, the force is, so we need to look to this. Look here, this is, we're going to deal with one bracing only, okay? Neglect the second one. Yeah. And consider that we are having the stability to be, or the stability bracing is going to resist movement to the right, as you can see. This movement is going to be delta, okay? This movement is going to be delta. The force that is going to be developed in the diagonal is going to be F. However, that the horizontal component that needs to be resisted or needs to be provided, okay, based on this force that is going to be developed in the bracing, this one is the lateral shear strength, lateral, okay, lateral. This is PBR. This is what the code is providing for us. But the real force that is going to be developed in the diagonal itself, it should be F, which is going to be related to the horizontal projection or the horizontal component by this theta. Okay, we're going to find that F cosine theta equals to, so F cosine this theta equal to PBR, right? So we have a relation between the axial tension that is going to be developed in the diagonal and the lateral shear strength provided by the code. Let's go back here. Okay, because PBR is the horizontal component of the brace force, this is F, okay? F equals to PBR over cosine theta, as we said, where theta equal to 10 minus 115 over 45. That's true. If we go back here, we have, this is 18 over 45. So if we're talking about, this is theta, for example. So we are having 10 minus 1, which is 18 over 45, right? 18 over 45, which gives us 21.1, 21.8 degrees. Then, based on that, we can say that the force is going to equal 0.4860, okay, which is already we have obtained. This is the required lateral shear strength over cosine theta. This would give us and provide us with the value of the force which is going to be developed in the diagonal. What is the meaning of this force? This is the tensile force needed, okay? The tensile force needed based on the requirement of the lateral shear strength based on the code, okay? Based on this code. Okay, so now we find that we need 0.52 kips, which is very small, but anyway, this is the amount that we need to provide. Okay, okay, so this is the force. This is the force that is going to be developed. Well, if this is the force, based on the limit state of tension, we're going to assume that the tension member, this member, is going to be under force. This force is 0.5234. Okay, this force is going to be resisted by tension, yielding. We are going to assume that the mode failure, or the failure mode, is going to be yielding in tension. Okay, as you know, in members in tension we have two different types of failure modes. Okay, we are going to assume tension yielding failure mode. So we are going to have F over 0.9 F yield, okay, wired area based on tension yielding. This is the area required based on tension yielding. F is known, F yield is known because we are dealing with 36 KSI F yield of the steel, and then we are providing the area. So this is the first condition here, that based on limit state of tension yielding, limit state of tension yielding. From AISC equation 6-2, okay, now till here we're talking about what exactly? Shear. We're talking about shear strength. Okay, we're talking about shear strength. From now on, we are going to talk about the required lateral stiffness. Lateral stiffness. Lateral stiffness means what? This point should not go more than delta. Okay, if the diagonal is going to move here, right? So actually here, this distance from here to here, it is going to be like small delta, for example. Okay, so we need to know, based on the required lateral stiffness according to AISC equation 862, we need to know how much that we should provide, or what is the area that should be required for this element, for this diagonal member, in order to maintain this required lateral stiffness. Okay, so from the equation A62, if you do not know this equation, please revisit the previous video. Beta BR equal to 1 over phi 2p r over LB. LB, it is the unraised length for the column. Know it is 18, and we're going to multiply by 12 for the conversion from foot to inch. Phi here, or phi, it is going to be 0.75. PR, it is 121.5, which is the total vertical load to be stabilized. Based on this, beta BR is going to be 1.5 kips per inch. So from here, we want to obtain, from this value, which is beta BR, which is the required lateral stiffness, we want to obtain what is the area that is needed, what is the minimum area needed in this case to fulfill this required lateral stiffness. So that we're going to compare the area here with this area coming from the lateral shear stress. Okay, so you understand the flow of the example. Okay, so now we have achieved this 0.016 area required based on tension yielding only for the case of required shear strength. But what the case if the required lateral stiffness is going to come true? This is what we're going to see in the next slides. So only to see if the lateral, this is the lateral movement of the structure. We want, in order to say that this diagram is providing stability bracing, we need to know what is the maximum delta that should be provided based on the lateral stiffness requirement of the code. So we are going to make this delta, capital or uppercase delta, is going to be used to calculate the longitudinal or the axial small delta here. Okay, because from here we can like make a relation based on the axial stiffness of the diagonal member, and then we can obtain the area required there. Okay? Let's see. Okay, the axial stiffness of the brace is given by F over delta, right? Let's go back here. Here we have F, here we have delta. So the axial stiffness of this diagonal equals to F over delta, force over the axial delta. It equals to what? E A over L, if I'm not wrong here. So we are going to find that this, we're going to look to it later, so we can put it like here. So F over delta equal to E A over L, right? We know L, we know the Young's modulus of the cross section. F is known for us, okay? Because this is the force that is going to be developed in the member itself. Delta, we are going to calculate it from this beta BR and from the other information that we have. From this equation, we can obtain E, which is the area required to fulfill the minimum stiffness requirement. Okay. Okay, so in this case, we're going to say that this delta equals to delta cosine theta, and this is right. So F, okay, where delta is the lateral displacement. So the axial stiffness of the brace can be written as F over small delta. This F, we know it, P BR over cosine theta over delta cosine theta. So you can find here it equals to P BR over delta times 1 over cosine theta squared. Or in short, we can put it like this. F over small delta times cosine theta squared equals to P BR over delta. If you look to this, this is F, this is delta. So this is the axial stiffness. And if you look to this point here, okay, if it goes here, okay, this is going to be delta. And the force, which is, we call it P BR, this is the force in this direction. So force in the horizontal direction over delta in the horizontal direction, this gives us lateral stiffness, right? Force over delta gives us lateral stiffness. Let's go back here to understand. So here F over delta, this is axial stiffness. But P BR over capital or uppercase delta, then it gives us lateral stiffness. Here we call this lateral stiffness. However, in this direction, which is the direction of the member itself, we call it axial stiffness. Okay, right? Okay, so based on that, we found that from the manipulation of the main equation, we found that one fraction is providing axial stiffness, another fraction is providing lateral stiffness, right? So we have two different stiffnesses for the same volume. They are connected by cosine square theta. Okay, from elementary mechanics of materials, the axial stiffness equals to EA over L, as I said to you. This is, I think that you know it from the basics of mechanics of materials, where that L is the length of the brace, and we know it well, is 18 by 12. Okay, and over sine theta, this is sine theta in this case, which is going to be, so here we have Let me stop here. So I think that, okay, so I think that here we can we can say that EA over EA over L, EA over L, which is the axial stiffness, which equals F over delta, times cosine square theta equal to, this is beta BR. This is from where? This one? It is from the equation from appendix 6. Okay, related to our case, to this type of bracing that we are using now. Okay, so it's stability bracing for columns, for example. 1 over theta, sorry, 1 over phi times 2p PR, 2 PR over LB. Okay, first of all, we can rearrange this equation, and we are going to find that area can be put in the left-hand side, and then we can obtain it. Let's clean everything here. So now we want A. This is our main concern. So this means that A, after rearrangement of this equation, okay, remember that this part, beta BR, we know it's 1.5. 1.5. From where we got it? From here. Okay, this is the required based on A-6-2. Required lateral stiffness. Required lateral stiffness. Okay. So based on that, we are going to have, based on that, we know this is the required lateral stiffness, 1.5. So we can obtain A, which means that after rearrangement, we can obtain A equal to 1.5 L over E times cosine square theta. If we substitute with all values, E is 29,000, and cosine squared, it is cosine 21, and L, it is going to be 581.6. And then we can obtain area. We can obtain the area that we are dealing with. This is the length of the brace, because we are talking about inclined brace. So we have here, this is the height is 18. So we are going to use this height and divided by sine theta in order to obtain the real length here, which is going to be 581.6 inches. And then we can substitute in this equation, we can obtain the area. So this is the required area for us. This is the required area for us. As you can see, if we go back here, you are going to find the required area here was 0.0162 based on lateral shear strength. However, here, the required area based on the lateral stiffness, shear stiffness, okay, it is 0.0349, which is larger than the lateral shear strength. This means what? The stiffness requirement controls. The results are typical in that the requirements are minimal. If you look at them, they are very small actually. 0.034 or 0.016. We're talking about very small values. So we are going to use a tension brace with a cross-sectional area at least 0.034, which is the maximum of them. So you can put something higher than this and it will be more than sufficient. Okay, this is for LRFD. We were using LRFD. So if you want to use ASD, then everything is going to be the same, except that for the area, we're going to use F over F field over omega instead of the phi. Okay, and the required stiffness is going to be beta. BR is going to be omega times 2PR over LB. But other than this, you are not going to find any difference at all between what we have done in LRFD and ASD. Okay, just to recap what I have done in order not to be confused with what we have done. First of all, we started with the lateral shear strength provided by the code in appendix. We're talking about column, okay? And Actually, we are talking about beam column if there is if there is flexural and axial forces. But here we are having axial forces only. So the beam column boiled down to be column only. And from the appendix 6, we can find for column, we are going to use here panel. We call it panel bracing. Okay, not point bracing. We are not going to use point bracing. So it is panel bracing. So go to the equation as I have explained in the previous lecture. It is related to the panel bracing, and you are going to find this PBR is going to equal 0.004 PR. Actually, in the code, you're going to find it 0.005, okay, according to the new edition 2016. Then, based on the lateral shear strengths, we are going to calculate the area required. We found this area to be 0.0162 for the bracing. Then up till here, we try to find lateral shear strength requirement. From here, we are going to use lateral or required lateral stiffness requirement. From the code A6-2 appendix 6, beta BR is going to equal 1.5. In this case, based on this, we are going to find that this is the required value, 1.5 kips per inch. Remember, this is stiffness, okay? Required lateral stiffness. Remember, lateral, as I said, not axial, it is lateral. Okay, we are talking about something. We want the structure, okay? This is delta, and there is force that is going to be there. This force, supposedly to be, according to this equation, it is supposed to be 1.5. Okay, so in this case, based on that, we are going to obtain the corresponding area here, and then compare it with this area. And this is what we have done in the next slide. So this is the area based on the lateral stiffness, and we found it larger than the area required for the shear strength only requirement. And based on that, we are going to use the larger value of them. This brings us to the end of this session. Thank you, and see you next time.